Hello people, welcome back to my channel. The topic for today's video is linear regression. We start with the decoding from the topic, that is we have linear and regression. Now first of all, what we need to keep in mind is that what do you mean by regression? Now regression, whenever you come across in any statistical books, it's defined as the best fit. Now best fit can be put before a line or it can be put before a curve. So given a set of some points, you have to find a best fit line or a best fit curve. It's always not possible that you fit a line. There can be a curve or some other exponential curves possible which can fit that particular line. Now say this is your y-axis and this is your x-axis. Now say I have some set of points here distributed in this way. Now what my linear regression will do is it will just fit a line like this. Now what do you mean by best fit, or how do you define this best fit? Now if you look at this plot, this scatter plot, what you can observe is the best first impression out of this, what you can get is the number of points that is covered by this particular line. So best fit essentially defines the maximum number of points covered by this particular line. And second definition of best fit is that it should reduce this error, that is a distance. So it can be this, 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 this and this. So what these distances are? These are essentially called as errors. So also this errors is called as the sum of squared errors. So minimize the distances between other points. So this original points was from my data set, and now I tried to fit a line, but my line says that your point should not be here. Instead, it should be here, so that it best fits all of this. So there is some kind of error in your prediction. So this essentially, this line which you model is called as your prediction. So whenever in the real world, if you want to predict something, you need to have some set of data. So that essentially is given by some equation. Say I am writing y is equal to x. We have y, we have x. We see what we write, we have y is equal to x. Now dependent upon this x value, y changes. So it is time independent. If it was time dependent, then you can say that this is a forecasting, like weather forecasting, but it changes accordingly irrespective of the time. So say now this particular line which you can see, it makes some angle with this x. Now say you draw some line like this. This angle is say some theta. Now you can generalize this as y is equal to 1 times x. Now you can generalize even more, y is equal to mx. Now what this m is nothing but your slope. Now what do you mean by slope? It is a rate of change of y with respect to x, that is y2 minus y1 upon x2 minus x1, which is your delta y by delta x. Also in terms of derivative, it is written as dy by dx. Now if you look into a trigonometric way, a trigonometric approach, if you construct a line like this, this theta is nothing but your opposite upon adjacent. So that theta is your sin theta upon cos theta, which is nothing but your tan theta. So if this value is 1 here, then your tan theta must be 45 degrees. So the theta value should be 45 such that tan of 45 is 1. So essentially your m, that is slope, is tan 45 degrees according to this. Now it's always not necessary that your line should be in this way, it can be this way, or it can be like this, like this. There are n number of possibilities, but your best fit definition is these two. This should satisfy in order to construct this line. So your equation will be now mx, and then you need to check whether what will be the value of y when your value of x is 0. X is 0 means slope is also 0. So say for example, I have one line which is like this. Now this also makes some angle, that is theta, with respect to this line. Now but here your x value is different. Here say your x value started from 1, this is 2, and this is 3. So you have different values of x. Now if your x value is 0, what will be the value of y? That is defined by some y-intercept, which you write it as c. So your equation of the line gets completed by y is equal to mx plus c, where m is the slope and c is your intercept. So what we can possibly do is we can just erase out this and we can be more specific. That is, x is called as the independent variable, that is idv, and this is your dependent variable dv. So essentially in linear regression, or whenever you try to fit a line, you first check what is the relation, or is there any correlation between this x and y. So in real world, when you collect different data points or data samples, or when you do linear regression or create your regressor, there will be some correlation among these data points. So now what you need to do is you need to model that regression, or you need to understand what is the interesting relationship between these independent and dependent variables. So now in this particular equation, you have only one independent variable, that is x, but in the real world there can be n number of different attributes or entities that can influence this y. So y is also called as your prediction, that is your line which you estimate. Now there is one concept. So say I am drawing this line again. This is your dependent variable and this is your independent variable. Now our goal is to find this particular line. So you cannot draw this particular line at the very first beginning. That is your task. So this is your model that you create this line, that is your prediction. Now you want to predict that. Now see how that is predicted. Now from this diagram, what is not visible is that your mean, average. So this is your x and this is your y. Say you consider a case of the height of some students or some population. So if a new person came and if you are asked to find the person's height, then you would have some prediction. So for that prediction, you need to calculate the average height of all those people in that particular population. So say I represent that average as like this. So since this cuts the x-axis, I'll represent it as x bar, and similarly I have some y bar. Now my regression line essentially passes through this, and then I have some set of points here which will be classified some this way or this way. Now say I am interested in knowing this point. So let us call this point as P1. Now this is your actual point and this is your line. Now your line says that there is a deviation of your actual point from this point by a distance of this much. So that essentially is your SSE, that is your residual that you call, that is your error. So this is nothing but your SSE. Now you can also see that there is another type of error which you can see, that is your average prediction from your this predicted. So this essentially is called as the regression error. So now what you do is you take this total and this one. Now you call this as the SST, that is the total sum of squares. So essentially your total sum of squares is consisted of the regression error SSR, I'll just represent, and by this SSE. Now SSE is also called as your residual error, and SSR is called as the deterministic error. Or in fact residual is also called as the stochastic error, which is seen in your model. Now let's try to focus more on this particular diagram, only on this quadrant. Now say you have some kind of prediction, you took the average and you have your prediction. So the difference of your actual point from your prediction, there is some error. Similarly, from your average values of all of this, you have some kind of error. Now your regression says that your point should ideally be this, that is, it should pass through that particular point. Now you can see that your this much portion which is seen, this is explained or this is covered by your linear regression or the regressor or the line which you are fitting. So you know why this particular error happens. Now you are unsure about why this kind of error happens. So this particular portion is unknown to the user and this portion is known. So your linear regression model can essentially explain why this deviation happens, but it cannot explain why this deviation is there. So it can be, there is one reason possible to this is you took those attributes which are irrelevant to your dataset, or you did not consider any correlation among those particular attributes. But in the real world, there may be some relation between those, but you fail to model or fail to feature engineer in your regression. That's why this deviation happens. And so this deviation is also in statistics called as statistical fluke. So now these kinds of information are very critical. So you cannot just put these kind of errors in your regression model. That's very biggest drawback of your regression. So you need to avoid such kind of errors. So now what we'll see is, we'll see how we can see the correlation among different data points when you have a large set of values. So essentially we told like you have some independent and dependent variable, so how they are correlated. So for that we basically use one correlation coefficient called as the Karl-Pearson correlation coefficient. So now what we have is our feature space consists of two types of variables, that is, one is independent and one is dependent variable. So if I want to represent it in a diagram, say like this, so this is my feature space, universe of features that are possibly there in my data set. So I have independent variables and then I have dependent variables. So only these two variables are present in my data set. Now say this is my IDV and this is my dependent variable. Now say in the real world we have some set of points, say this is dispersed in this way. Something like this, a few set of points. We are interested in knowing what is the relation between dependent and independent variables. Now you can see that there is particular kind of dispersion that has happened. There is no particular trend. There assumes to be a symmetric between these all data points. Now what we'll do is we'll just construct a circle around this. Now we'll just divide this particular region of this data points into some quadrants. So this I know, this is my first quadrant, this is my second quadrant, this is my third quadrant, and this is my fourth quadrant. Now this is from trigonometry, we get these things. So what we basically see is we need to estimate the relation or correlation between this x and y, that is dependent and independent variable. So the Pearson or the Karl Pearson coefficient is represented by this Rxy. Small r represents the Pearson coefficient, and x and y between two independent variables. It is given as summation of xi minus x bar into yi minus y bar upon summation of xi minus x bar square into square root of summation of yi minus y bar square. So now what we need to do is we need to estimate the area of each of these points. So you know that in this quadrant you have everything as positive and positive. Here you have everything as negative and negative. Here you have positive and negative. You have negative and positive. So that is simple. You can see in this way. You have this positive y-axis, positive x-axis, that's why you have positive positive. You have negative x-axis, positive y-axis, that's why positive, negative and positive. You have both negative x and negative y, that's why both are negative. One is positive x-axis and you have negative y-axis, that's why it's positive and negative. Now if you consider any one particular point, that is, say for example, I am interested in this point. So if I want to calculate the area of this particular region, so what I will do is I will just construct a rectangle around this. So which is nothing but our y2 minus y1 and x2 minus x1. So this is our x2 minus x1 and this is our y2 minus y1. If you see, this forms a rectangle. If I were to calculate the area of this rectangle, I would do area is length into breadth. So similarly, you need to calculate x2 minus x1 into y2 minus y1. So that is nothing but your numerator. So you have both positives here in this region. Similarly, if you see in the opposite region, say I am interested in calculating the area of this point. So what I draw is, I draw a line like this. I know the area of this region is y2 minus y1 and x2 minus x1. So here what you have is, you have both negative and negative. So negative multiplied by negative quantity is also a positive. So you have these two positive regions. Now here what you have is, in this region, if you calculate the area of this, you have something that is negative and positive. Similarly, you have positive and negative. So area of these two regions are negative and negative, and these two are positive and positive. If I were to calculate the correlation of this given data points in this particular topology, I would get the correlation coefficient of this xy as 0. Why? Because you know it's mathematically coming out 0, means it is neutralizing. So in the real world, you don't see any particular points which are dispersed in this way, or the probability can be very low or it can be 0. So everything in this world, whether it's a data set or anything, you have some kind of correlation between these data points. So any particular correlation which seems to be like this is false, that is a statistical fluke. Then conversely, what you can have is, you can have the same set of points, but now here your points is dispersed in this way. It need not be always a straight line, but we can make. So here what we see is, you have both lying in the positive regions. So now this is your area. So by this, if you estimate, your Pearson coefficient between Rxy comes out to be 1. Means when x value is increased, y value is also increasing accordingly with it. So that means you have a positive correlation. And similarly, if you just consider the other regions, that is, if you have points in this space and you have points in this space, if you construct like this, you have negative and negative, both are negative, your R xy is -1. So essentially, what is the range of your correlation coefficient? So correlation coefficient ranges from -1 to 1, where 1 means your data points or relationship between the dependent and independent variables is negative. If it is 1, they are highly correlated, and if it is 0, then that happens to be by a chance, means that not present in the real world. So with this estimate, what we have is we have basic 4 assumptions which we always follow in our linear regression. So first assumption is that there is assumption of linearity. What do you mean by linearity? Means there is some linear correlation of these data points between your dependent variable and independent variable. So that means it should be like this or like this, but it should not be this way. Why? Because there is no correlation. And second is that it assumes normality of errors. Now what this means is whenever you have a distribution of this data point, say the distribution of this on this axis follows a normal distribution, on this axis it follows a normal distribution. So there should be a normal distribution of this errors which is followed. Now this normal distribution can be modeled by, say, for some histograms, you can model this way, or you can also plot a curve between your predicted values and your residual values. That is nothing but your regression error versus your sum of squared errors. Third one is that it assumes independence of errors. So you have 2 dimensions, one dependent variable dimension and independent variable dimension. So the errors in one dimension is not influenced by error in other dimension. So there is no kind of correlation among these errors which are there happening. And fourth one, what you have is something called as assumption of homoscedasticity. Now what do you mean by this homoscedasticity? Homoscedasticity means, say you have a distribution like this, your points should always follow a uniform distribution, something like this. It should be uniform. The rate how it spreads, the rate of spread should be uniform, and it should not form something like a cone. Cone shape means you're starting with a few points, but when you just move ahead or when your x value increases, it will just disperse. So by this what happens is your variance will increase. So now variance is nothing but what we saw, our total error, that is we have our SSR plus SSE. So which is also given by your y minus y bar square 1 upon n. Now this brings you to another algorithm that we have seen, that is gradient descent. So essentially your error or your cost is dependent on your y predicted or y bar, which is nothing but your m and c. So in order to carry out linear regression, you use different kinds of algorithms. So one approach is by using gradient descent, by way you can find the best line that passes through all these data points by satisfying the best fit criteria. So well, that was all regarding the linear regression in machine learning. So hope you guys enjoyed this video. If you want to get educated watching this video, please do like, share, comment, and if you are new to this channel, please consider subscribing. Thank you very much for watching this video.